Hello, welcome. This is Physics 104A homework solutions for Chapter 14 on wave motion. Number 16, an ocean wave has period 4.1 seconds and wavelength 10.8 meters. Find its wave number and angular frequency. So the period I've listed out, 4.1 seconds, wavelength lambda, and we want to know wave number k and angular frequency omega. And we'll go to those formulas, those relationships. K is 2 pi over the wavelength, and so that's 0.582 over meters. And the angular frequency omega is 2 pi over period, so that's 1.5 per second or radians per second. Number 18, ultrasound used in a medical imager has frequency 4.86 megahertz and wavelength 0.313 millimeters. Find the angular frequency, the wave number, and the wave speed. So I've written out the given information, make sure it's in MKS units, so 0.313 millimeters is 0.313 times 10 to the negative 3 meters. Omega is 2 pi times frequency, and that gives us 3.05 times 10 to the 7th radians per second. And the wave number, k, is 2 pi divided by lambda, so that's 2.01 times 10 to the 4th over meters. It then asks for the wave speed, and we can get that by doing wavelength times frequency, and we should get 1520 meters per second. You can also check that because wave speed is omega divided by k, so angular frequency divided by wave number, and that should also give you 1520 meters per second. Number 21, the main cables supporting New York's George Washington Bridge have a mass per unit length of 4,100 kilograms per meter and are under 250 meganewtons tension. At what speed would a transverse wave propagate on these cables? It's giving us the linear density, 4,100 kilograms per meter, and it's already in MKS units very conveniently. And the force is 250 times 10 to the 6 newtons. So the speed of a wave propagating is the square root of the tension force divided by mu, and you should get 250 meters per second. Number 22, a transverse wave 1.2 centimeters in amplitude propagates on a string. Its frequency is 44 hertz. The string is under 21 newtons tension and has mass per unit length of 15 grams per meter. Determine its speed. All right, so we have amplitude 1.2 centimeters. Frequency is given the force, tension force, and mu. And if you look at the formula, it doesn't matter what the amplitude is, what the frequency is. All that matters is the tension force over mu. Just make sure you get an MKS unit. So 21 newtons over 15 times 10 to the negative 3 kilograms per meter, and we get 37 meters per second. Number 24, a rope is stretched between supports 18.3 meters apart. Its tension is 78.6 newtons. If one end of the rope is tweaked, the resulting disturbance reaches the other end 585 milliseconds later. Find the rope's mass. All right, so we're given the length, we're given the time for the wave to travel that length, and we're given the tension force. So we know these equations involve speed, so let's get speed. Speed is the length divided by time, 31.282 meters per second. And we know from the formula, if you look up at number 22, speed is square root of tension force divided by mu. So solve that for mu, and you get mu is tension force divided by v squared. And when you plug in the tension force and the v, 0.08032 kilograms per meter. And now the question wants to know, what is the mass? Mass is linear density times length, and you should get 1.47 kilograms. Number 42. A surfer paddles out beyond the breaking surf to where waves are sinusoidal in shape, unlike the one shown on this picture, with crests 59.6 meters apart. The surfer bobs a vertical distance of 4.28 meters, taking 3.09 seconds to go from trough to crest. Find the wave speed and describe the wave using equation 14.3. All right, I've listed out the given information. There's lambda, there's amplitude. Let's look at how I got the amplitude. The surfer bobs a vertical distance of 4.28 meters. So that is from the trough up to the crest. Remember that amplitude is only half of the full height. So half of that, 2.14 meters. Now let's look at the period. It says that going from the trough to the crest is 3.09 seconds. Now that is only half the wave. That's half the period. So double it and you get the period of 6.18 seconds. And now we are equipped to find the speed of the wave. That's frequency times wavelength, or wavelength divided by period, because remember frequency and period are reciprocals of each other. So you should get 9.64 meters per second. Now we're going to make an equation for this wave, and it says in the problem using equation 14.3, so that's the equation. The format is where my red pointer is. We're going to need k and we're going to need omega. So k, the wave number, is 2 pi over lambda, 0.1054 per meter. Omega is 2 pi over period, so you should get 1.0167 radians per second. And now let's plug all these values into the equation. We have the amplitude, we have kx minus omega t, so you should get y as a function of x and t is 2.14 cosine of 0.105x minus 1.02t. I've rounded these to 3 significant figures, and the units are in meters and seconds. Number 47, a Doppler effect problem. The speed limit on a highway is 95 kilometers per hour. A car whose horn emits 352 hertz sound is approaching you. What frequency will you hear if the car is going at the speed limit, assuming a sound speed of 343 meters per second? All right, we need to get this in MKS units, so the speed of the source for the equation we use V sub S is, and you should convert that, 95 kilometers per hour. You should get 26.38 repeating meters per second. Speed of sound, 343 meters per second. The emitted frequency is 352 hertz. We're going to use the equation for a source that is moving, the source of sound that is approaching. And it's this equation that f prime, so the perceived frequency is f over 1 minus speed of the source over speed of sound. You should get 381 hertz. Number 53, light intensity 3.3 meters from a lamp is 0.73 watts per meter squared. Find the lamp's power output, assuming it radiates equally in all directions. All right, so we're dealing with a spherical wave. We're given the intensity of 0.73 watts per meter squared at a distance of 3.3 meters. We're going to use this equation. Intensity is power that is spread out over 4 pi r squared. That's the surface of the sphere. And so solve that for power. Power is intensity times 4 pi r squared. Make sure you've got everything in MKS units, which you do, and it should be 100 watts. Number 59. At a point 15 meters from a source of spherical sound waves, you measure the intensity 750 milliwatts per meter squared. How far do you need to walk directly away from the source until the intensity is 270 milliwatts per meter squared? Let's write out the given information. R1, 15 meters, intensity 1 is 750 milliwatts per meter squared. R2 is question mark. That's what we want to solve for. And I2 is 270 milliwatts per meter squared. Intensity is power divided by 4 pi r squared. Let's do the technique where we take this equation, put the things that are changing to the left, the things that remain constant to the right, and the things that are changing are intensity and distance. So algebraically, getting those over to the left, we have IR squared equals power over 4 pi. That means that IR squared equals constant. So with that information, we say I2 R2 squared equals I1 R1 squared. And now we can disregard power. We don't need to solve for power. We are going to solve for R2. So R2, solving algebraically, you should get square root of I1 over I2 times R1. And we're going to plug those in. Now that square root of I1 over I2 is the square root of 750 over 270. We don't need to get those in MKS units. Milliwatts is fine. As long as the units are the same, they will divide out, and we're just left with that ratio, times R1, which is 15 meters. So the final distance is 25 meters. So our initial distance was 15 meters. Final distance is 25 meters. The question asked, how far do you need to walk directly away? So to go from 15 meters away to 25 meters away, you have to walk 10 meters farther away. Number 64. What are the intensities in watts per meter squared of sound with intensity levels of 65 decibels and -5 decibels? We're going to use the decibel equation. Beta is 10 times logarithm of intensity over the threshold of hearing, which is 10 to the -12, and those units are in watts per meter squared. And we want to solve for the intensity with given beta amounts. And so let's go through the algebra to solve for I. First, we're going to divide both sides by 10, and that gives log of I over 10 to the -12, but I'm dividing that logarithm up into the difference of two logarithms. So remember, the logarithm of a ratio is the difference of two logarithms, log of I minus log of 10 to the -12. So we have beta over 10 equals log of I minus the log of 10 to the -12 is -12. So minus -12, that becomes plus 12. So I'm switching left hand and right hand, getting the intensity on the left hand side. So log of I is beta over 10 minus 12. And we want to solve for I. So let's turn this into an exponential equation with a base 10. That log without any base written means base 10. So that means that 10 to the beta over 10 minus 12 equals intensity. And now we are free to, with this equation, plug in whatever beta values we want, and we'll get the intensity. So intensity for 65 decibels, beta is 65. That's going to be 10 to the 6.5 minus 12. You can follow through with that and get 3.2 times 10 to the -6 watts per meter squared. And then for the second part, it says for -5 decibels, so that beta over 10 is going to be -0.5 minus 12. So 10 to the -12.5 is 3.2 times 10 to the -13 watts per meter squared. Because it is a negative decibel, that just means it's below the threshold of hearing. So it's below 10 to the -12 watts per meter squared. Number 66. Sound intensity from a localized source decreases as the inverse square of the distance according to equation 14.8. If the distance from the source doubles, what happens to the intensity and to the decibel level? So if it varies inversely with the square of the distance, if the distance doubles, then the intensity will be cut by a factor of 4. But let's go through the math to see that. Let's set up a ratio of the intensities. Final intensity over initial, so I2 over I1 is P over 4 pi R2 squared divided by the reciprocal, so we'll say times 4 pi R1 squared divided by P. A lot of stuff divides out. The P divides out the 4, the pi, and we're left with R1 over R2 squared. Now we're going to replace R2 with 2R1. So we have R1 over 2R1. The R1s divide out. We're left with, in these parentheses, 1/2 squared, which is 1/4. Now, it also asks us what happens to the decibel level. The difference in decibels, we're going to use this equation for delta beta, is 10 times logarithm of the final intensity over the initial intensity, and we already know that that ratio is 1/4. So 10 times the logarithm of 1/4 is negative 6.02 decibels. So the decibel level decreases by 6.02 decibels. Number 67. At 2 meters from a localized sound source, you measure the intensity level at 75 decibels. How far away must you be for the perceived loudness to drop in half? That is, to an intensity level of 65 decibels. All right. So we have R1 is 2 meters, beta 1 is 75 decibels, R2 is question mark, that's what we're solving for, beta 2 is 65 decibels. And so given that we know the two different betas, and ultimately we want to solve for R, let's see what happens with intensity. So delta beta, which is beta 2 minus beta 1, final minus initial, is 10 times the logarithm of I2 over I1. Difference of the betas, 65 minus 75, that's negative 10. And we continue with equals 10 logarithm I2 over I1. Divide both sides by 10. And so we have negative 1 equals logarithm of I2 over I1. We're going to come back to this. Let's see what happens with I2 over I1. Specifically, we want to start to involve the distances because we're given things in terms of R. So here I've done in the green ink, I2 over I1 is P over 4 pi R2 squared divided by P over 4 pi R1 squared. Things divide out and you're left with R1 over R2 squared. All right, so now back to the blue ink. You notice up here I've done logarithm of I2 over I1. Now let's replace that I2 over I1 with R1 over R2 squared. One of the rules of logarithms says when you're taking the logarithm of a number and it has an exponent, you can take that exponent and move it as a coefficient of the logarithm. So that becomes 2 times the logarithm of R1 over R2. Divide both sides by 2. Again, we are getting at R2. So step by step, we are algebraically getting that R2 isolated. So we'll divide both sides by 2. We have negative 1/2 equals logarithm of R1 over R2. Now that you've got a simple logarithm equation, turn it into an exponential equation. So remember, when no base is written, right where my marker is, that means it's a base of 10. So turning it into an exponential equation is 10 to the negative 1/2 power equals R1 over R2. We're almost there. Let's solve it for R2. So R2 is R1 divided by 10 to the negative 1/2 power. Now we can plug in R1 of 2 meters, divide by 10 to the negative 1/2, and we get 6.3 meters. And that is the end of the chapter 14 homework. I hope you have a great day.